Hi everyone. We are going to go over projectile motion. Projectile motion is the combination of horizontal motion and the vertical motion. So if I throw this chalk upward, let me take a small piece here. If I throw this chalk upward and then catch it, that's the vertical motion. If I roll it on that table and it rolls down the table, that would be a horizontal motion. However, if I project it this way, that it goes in a angle, making and landing somewhere. This type of motion, where it's horizontal and vertical at the same time, it is studied under projectile motion. In case of projectile, how far it is going to land, there are a lot of factors which affect that. There could be initial velocity, there could be the angle at which it is projected. So a simple description of the projectile motion is let's start with a picture. It's a flat horizontal surface and an object is projected. You could think of a real life example as a ball is kicked in the air from the ground, and this ball goes up with some velocity. There is no need right now to draw the ball and give the description. However, in some problems you can actually draw the object and give the description or draw the diagram. It moves with the initial velocity which is given to it by the kick and making some angle. We can call it theta. This velocity initially has two components, and like I told you in previous video, these two components are going to be v naught x and v naught y. We know this v naught x, let me write it here. V naught x is equal to cosine of theta. V naught y would be equal to v naught sine of theta. Okay. What is v naught? V naught is the initial velocity which is given to this object, or let's say football. Now we know that this football, since it is projected at some angle, it's not going to go straight horizontal or vertical. So it moves, instead it will move on a horizontal curved path, and it will land somewhere on the ground at the same level. In this projectile, it will land on the same level. However, it can land anywhere. Maybe there was a building here and it can land on the building. This distance is defined as the range of the projectile, how far it is landed. And the velocities, we already have them in there. At the highest point, what happens to the velocity? Does it go to 0? Overall velocity? No. Only the vertical velocity that goes to 0 when it is here. Its horizontal velocity remains the same. So if I draw projected to other positions, Vx, Vy, Vx, here Vx, Vy becomes negative, and then further here it would be longer, and then Vx. If you notice, Vx remains the same throughout. That does not change. Vx is the velocity at some time later. Vx remains constant. What does it mean? Does it tell us some information about the acceleration? It tells us that the ax is 0. Why Ax is 0? Because there is no force in the horizontal direction. There is only force acting on this football vertically, and that is a gravity. There is only one force or acceleration acting on it, that is negative g, which is downward. It is exactly the same, the vertical motion is exactly the same as you have learned in the free fall vertical motion. You throw something upward, it's coming back down. When it is going upward, it is slowing down, velocity is getting, the velocity is getting smaller. When it's coming back, it is speeding up and it's increasing. And the Vx, Vy changes. However, it changes such way that A is equal to negative g. So it is under effect of negative gravitational acceleration all the time. So if someone asks you, what's the gravitational acceleration here? It's negative g. What it is here? Negative g. Negative g. Throughout its motion, it is moving under gravity. All right. So horizontal component remain constant, and there is no acceleration horizontally, but there is a horizontal value for the velocity, but it is a constant value. There is no acceleration. There is a vertical component that is constantly subject to change because of the gravitational forces acting on it, and it is under the effect of the acceleration due to gravity. This changes our kinematics equation for free fall motion. We have to divide these into two: horizontal motion, which is in a straight line, and then the vertical motion. For horizontal motion, we can use the same equations that we know already for finding the displacements, horizontal displacement and initial velocities. So for the x, I can write as x naught plus vxt. That's a kinematic equation. Vx is equal to v naught x, because velocity is constant, Ax is 0. Okay. We can also write the delta x, total horizontal displacement, is equal to, which will give me the same equation that I can get from the basic definition for velocity. But since we have those equations, we can use them. That's going to be v naught xt minus half axt squared. Since ax is 0, you only have v naught xt delta x. That's the formula for the range. How far it will lend, what's the horizontal displacement covered. If you notice, this formula is the same as this one. They both lead to us the basic definition of velocity and this second equation of kinematic that lead us to the same formula for range. If it is the velocity has a component, you can further split it cosine of theta multiplied by t. Okay, t is the time it stays in the air or time of flight. Time of flight is the time it stays in the air. For vertical motion, we can use the same equations that we have used here. However, x will be replaced by y's. Definition of averaged velocity. Second equation, Vy, vertical velocity at some time later would be equal to V naught y minus gt because ay is equal to negative g. Then the next one would be delta y v naught yt minus half gt square. Remember, we use negative in the equation instead of plugging in negative 9.8 meter per second for g. We change the equation. And the last equation, vy square v naught y square minus 2g delta y. If you further explain them, you can replace the initial velocity by its value. You can write down v naught sine of theta here, and you could do the same thing here, and you could do the same v naught sine of theta in this equation. But we know that if theta is 0, you will have the vertical component of the velocity. However, if theta is 0, that you have projected something horizontally. So in this case, for example, if you have projected the projectile horizontally, you have some sort of launcher here, and you have projected it horizontally. This one would have initial velocity for sure because it's being projected horizontally. However, its initial vertical velocity is 0. Okay, it's like it's being dropped vertically. The time of flight should remain the same in both cases. If you drop the object, the time it takes to reach here, it should be the same as you project it and land at some distance. The time should remain the same. Because there is only one force acting on it, that is vertically on both situations, and if vertical motion, the time it will take to cover this distance, that should remain the same here, because the force, vertical force, that is the only force. There is no horizontal force which can change the time here. There are some complementary angles which can generate the same range. Like if you project at 30-degree angle and 60-degree angle, they both are going to land at the same point. So at projection at 30 degree, that definitely looks bigger than that. Let's make it 60 degree, and the projection at 30 degree, they both will land on the same, the complementary angle. They can produce the same range. Now we have the derivation of the formulas like the time of flight, physical quantities related to projectile, the range of the projectile, maximum height reached, time to reach the maximum height, and there is a derivation of different formulas for symmetrical motion of the projectile, which you will see in my next video. So I'm going to stop here. Hello everyone, I'm going to cover a problem for projectile motion. I have written the problem here. A rescue plane dropped some goods for the climbers which are struck on the top of a cliff, and that cliff is about 235 below the location of the helicopter. If the plane travels horizontally, only horizontally, at 250 km/h, how far in advance the goods should be dropped? First of all, what is given to you? It's the initial velocity. So we can write down initial velocity is equal to 235, the initial velocity is 250 km/h. Now this one is in the set of units where we would like to convert it to MKS system. So convert this to 250 multiplied by 1000 meter divided by 3600 second. and you can get the value in meter per second. The value in meter per second is going to be 250 times 69.4 meter per second. Okay, that is given. And the other one, this one is in meters, so there is no need to do any conversion. We have the vertical height, which is delta y equal to 235 meter. These are the two pieces of data given directly. There is something I would like to add here. Since it is only horizontal, I can put the x here because this is the horizontal component of the velocity, and this should remain the same throughout its motion. There is no vertical velocity, so there is no need. We don't have any vertical velocity. There is no v naught y. That is 0. That is the hidden information given in this problem, that initial velocity is 0. Now we can use the formulas, some from the horizontal motion and some from the vertical motion, combine them and get what we need to find in this equation, which is the range. How far in advance the goods should be dropped? That is the question about the range. If I draw this whole problem here, that is going to look like something. The plane is here, it drops a good 235 below. That's negative from its own location. This is going to be negative. It drops. However, the goods take the horizontal path, the projectile path, and they get dropped at the distance which we are interested to know. We know that how fast these goods were dropped. They were dropped at 69.4 meter per second. All right. So once we have this given, what we need to know, we have initial velocity horizontal, we have the vertical distance, we have the value for the vertical velocity initial, that it is 0, and then we can put them together in order to find the range. In order to find the range, as if we look at the formulas, I'm going to erase it. And I will start by using the range equation that I know, that is delta x is equal to v naught x multiplied by time. Now I do have v naught x, which is 69.4, however I do not have the time it takes for the goods to reach the ground. In order to find the time, I really don't have any other equation that I could use for horizontal motion. So for that I have to rely on the vertical motion because time should be the same for both. So delta y vertical motion equation, where because the distance is given to me, so for me it would be convenient to use delta y and something which includes the displacement and the time. V naught yt minus half gt square. Now I already mentioned that this one should be equal to 0, so our equation further simplifies to negative half gt square, and by plugging in negative 235 here, this becomes half gt square. Negative gets cancelled. By rearranging the equation, I can find time, and time will be equal to two times 235 divided by g and then the square root. You can use your calculator to find that out. The 235 multiplied by 2 divided by 9.8, that gives me 47.9, and then square rooting it, it gives me 6.9 seconds. Now I have the time of flight. It has given me the time the goods will take to go from here to here. I can use this in my equation So my previous equation is delta x, V naught x is 69.4 times 6.9. This is in meter per second. This one is in second. So second get cancelled, you will get your answer in meter, and this is what you should have. This is going to give me 480 meter delta x, or the range. This much in advance, the goods need to be dropped for the climber to get them. Let me know if you have any questions related to this problem.